Unit 2, Artificial Neural Networks. In this unit, we are going to see the multilayer perceptron, also called as MLP. This is a type of neural network composed of multi-layers of interconnected neurons. Each layer transforms the input data through learned weights and biases, enabling the model to capture complex patterns. Next, we have the activation function. This is the mathematical gate that decides whether a neuron should fire. Common functions like ReLU, sigmoid and tanh introduce non-linearity, allowing networks to learn intricate relationship beyond simple linear mapping. To train these networks, we use the backpropagation algorithm. This method calculates the gradient of the loss function with respect to each weight by the chain rule, enabling efficient updates through gradient descent. But how do we choose the best model? That's where the model selection comes in. Techniques like cross-validation helps us to evaluate different architectures and hyperparameters to find the most effective configuration for our data. Then next topic is regularization. This is a strategy to prevent overfitting. Overfitting is nothing but when your model performs well on training data but poorly on the unseen data. Regularization techniques adds penalties to the loss function to discourage overly complex models. One such technique is a white decay. So white decay which reduces the magnitude of weights during training. By shrinking weights, we promote simpler models that generalize better. And finally, dropout. This method randomly disables a subset of neurons during training, forcing the network to learn redundant representation and reducing reliance on any single path through the network. Together, these concepts form the backbone of robust, scalable machine learning systems. Understanding these concepts is a key to build a model that are not only a powerful but also a reliable. Let's start with multi-layer perceptron. So it is the building block of deep learning network. An MLP is a type of artificial neural network composed of multi-layers of neurons, each designed to transform data in increasingly complex ways. It starts with the input layer, which receives the raw data, that is the features, the number of categories that describe each data point. Next, hidden layer. These are where the real computation happens. Each neuron in a hidden layer performs a weighted sum of its inputs and then applies an activation function. It introduces the non-linearity and enabling the network to learn the patterns. Then finally, output layer. The output layer which produces the final prediction or classification result, whether it's identifying an image or forecasting a value or making a decision. Each neuron in one layer is connected to every neuron in the next, which allows the network to model complex relationships between inputs and outputs. Together, these layers form a flexible and powerful system capable of learning from data and making intelligent predictions. And this is the architecture layer of multi-layer perceptron. We begin with the input layer, which receives the raw data. As we said, these are the features that describe each example. Next, we move through the one or more hidden layers. These are the computational engines of the network. Each neuron in the hidden layer receives input, applies a set of weights, adds a bias and passes the result through an activation function. This process allows the network to learn non-linear relationships like patterns that simple linear models would miss. Then finally we arrive at the output layer which delivers the final prediction or a classification result. This layered architecture like input, hidden and output is what enables neural networks to tackle the complex tasks like image recognition, language translation and decision making with remarkable accuracy. Then the next topic is overfitting and underfitting. Let's start with overfitting. So overfitting happens when a model memorizes the training data too well, even the noise or outliers occurs. As a result, it performs brilliantly on known data but fails miserably on new or unseen data. For example, if a student who memorizes the answers without understanding the concepts. Then next one is underfitting. So underfitting occurs when the model is too simple to capture the underlying patterns in the data. It struggles even with the training set, leading to poor performance across the board. For example, if you are trying to fit a straight line to a complex curve, so it does not work. It does not work. To avoid these both extremes like overfitting and underfitting, the model selection is used. So it is the process of choosing the right architecture and level of complexity for the task at hand. Hand techniques like cross validation, grid search and performance metrics, which helps us to calculate or evaluate the different models and pick the one that strikes the best balance between bias and variance. Next, hidden layers. It is a powerful modeling approach, the direct input to output mapping. In this, inputs are transformed directly into output through a single affine transformation. Single affine transformation is a weighted sum of input plus a bias. So this is followed by a softmax operation which converts the raw scores into probabilities for a classification tasks. The key assumption here is that the labels we are trying to predict are truly affine functions of the inputs. If in that case this model is not only sufficient, it's a optimal. But here, the linearity is a strong assumption. So real world data is rarely that simple. From images and speech to financial trends and medical diagnostics, the relationship between inputs and outputs are often non-linear and complex. That's why more advanced models like multi-layer perceptrons with activation functions are essential. So they allow us to capture the richness of real-world patterns and deliver a better accuracy. Overcoming linearity hidden layers in neural network. So the limitations of linear models. Linear models rely on affine transformations, that is a weighted sum of input plus a bias. While this approach is simple and efficient, it falls short when dealing with complex patterns in data. Why? Because affine transformations are inherently linear. They assume that the relationship between the input and outputs can be captured with straight lines or flat planes. But in real world data, it is rarely that simple. From image recognition to natural language processing, the patterns we need to learn are often non-linear, twisted, layered and intricate. That's why we need non-linear representations. By introducing activation functions and stacking layers in neural networks, we enable models to bend, curve and adapt to the true shape of the data. In short, linear models are a great starting point, but for a deeper understanding and better accuracy, non-linearity is essential. And this is the architecture of an MLP with hidden layers of 5 hidden units. Uh, an MLP is a type of artificial neural network and composed of a stack of layers. The input layer receives the raw data, features like here the x1, x2 and x3 and x4, and one or more hidden layers we can use here. So here it performs the computations. Each neuron applies a weighted sum, adds a bias and passes the result through an activation function. The output layer produces the final prediction or classification represented by the nodes like O1, O2 and O3. This fully connected structure enables the network to learn non-linear relationships which are essential for modeling real-world data. Let's talk about the simpler models. In some cases, inputs are mapped directly to outputs using a single affine affirmation, which is followed by a softmax operations. This works well if the labels are truly linear of the inputs. But here the limitation is linearity is a strong assumption. So affine transformation alone can't capture complex patterns. That's why we need a nonlinear representation. So nonlinear representation is used to model the richness of the real world data. As we train these models, we face two common techniques. As we said, overfitting and underfitting. So overfitting is the training the data. It memorizes the training data but fails on new data. And underfitting, this model underfitting is too simple and misses the important patterns. To strike the right balance, we use the model selection, like choosing the right architecture and complexity. This involves testing different configurations and evaluating performance to find the best fit. So the neural networks are like MLPs with their layered structure and non-linear capabilities, which gives us the flexibility to learn from data and make accurate predictions. So the next one is activation function. So it is the most important component in neural network. Activation function which decides whether a neuron should fire or stay quiet. They take the weighted sum of inputs, adds a bias and use them to make a decision. In doing so, they transform inputs into outputs, passing meaningful signals forward through the network. Why they matter? Most activation functions introduce non-linearity, which is crucial. Without non-linearity, no matter how many layers we stack, the network would just be performing deep linear math. That means it would not be able to learn complex patterns or represent to difficult to find the relationship in data. Activation functions are also differentiable, which is key for a training. During a backpropagation, we calculate gradients to update weights, and that's only possible if the activation function allows us to compute the derivatives. So, activation function are differentiable. In short, activation function are the gatekeepers of the learning. They give neural networks the power to go beyond simple logic and tackle the complexity of the real world. Let's talk about common activation functions. First is ReLU. ReLU is a rectified linear unit. It is super simple. If the input is a positive, it stays. If it is negative, it turns to 0. This helps our model to learn fast and work well with big data. Next one is sigmoid. So sigmoid function, it turns any number into something between 0 and 1. This is helpful when we want to say how likely something is, like whether an image is a cat or not. Then we have tan h. Tan h is a short for hyperbolic tangent. So it is like a sigmoid, but it gives values between -1 and 1. This makes it better for models where we need both positive and negative outputs. Finally, there is a softmax. So it is used at the end of classification models. It takes all the inputs and turns them into probabilities that add up to 1. So we can say this image is 80% likely to be a dog and 20% likely to be a cat. These functions are at the heart of deep learning. They make neural network powerful and able to learn from all kind of data. Let's dive deep into ReLU function. So ReLU stands for Rectified Linear Unit. It is introduced by Nair and Hinton in 2010. ReLU, which quickly became the go-to activation function for modern neural networks. Why? Because it's incredibly simple to implement and delivers a strong performance across a wide range of predictive tasks. Here is how it works. So ReLU applies a non-linear transformation by outputting the input directly if it is positive and 0 if it is not. So mathematically it is defined as ReLU of x equal to max of x comma 0. So you can think of ReLU as a filter that retains only the positive values and discards all negative ones by setting their activations to 0. This simplicity makes ReLU computationally efficient, and its non-linearity allows neural networks to learn complex patterns without the vanishing gradient issues that plague our older functions like sigmoid and tanh. So here is the derivative of a ReLU function. So the ReLU or a rectified linear unit which makes the derivative simple and efficient to compute. For input values where x is greater than 0, the derivative is 1. And for input value where x is less than 0, the derivative is 0. At x equal to 0, ReLU is not differentiable. So there is a sharp corner discontinuity. But here is the practical insight. During training, exact values of 0 are rare. So we typically set the derivatives at 0 to 0. This simplification works well in practice and does not affect the model performance. In engineering context, this discontinuity at 0 is considered negligible. The piecewise nature of ReLU allows for fast computation and effective gradient flow, which is why it remains the most popular activation function in deep learning. ReLU function. So ReLU function is also called as a rectified linear unit. It has become the most popular activation function in deep learning. First, ReLU has well behaved derivatives. The output is either 0 or the output itself, which makes it simple and efficient to compute during training. This simplicity leads to improved optimization. ReLU enables faster and more stable training, helping models converge quickly without getting stuck. One of its best advantage is that it mitigates the vanishing gradient problem, a common issue in older activation functions like sigmoid and tanh, where gradients shrink and learning slows down in deep networks. Now let's talk about a powerful variant, parameter ReLU or p-ReLU. Unlike standard ReLU, p-ReLU allows a learnable slope for negative input values. This means the model can adapt how it handles negative activations during training. Mathematically, it is defined as p-ReLU of x equal to max of 0, x plus alpha into minimum of 0, x. Here alpha is a parameter that the network learns, giving it more flexibility and potentially better performance. In short, ReLU and its variants are not just activation functions. They have optimization accelerators and gradient stabilizers. They are a big reason why deep learning works so well. Next is sigmoid function. It is one of the classic activation function in machine learning. The sigmoid function maps input values from negative infinity to positive infinity into a smooth range between 0 and 1. Mathematically, it is defined as sigmoid of x equal to 1 by 1 plus expression of minus x. So why it is used? Sigmoid acts as a squashing function compressing any real valued input into the 0, 1 interval. This makes it especially useful for modeling probabilities and for binary classification tasks. It is also smooth and differentiable, which is essential for gradient based learning methods like backpropagation. The smooth curve allows gradients to flow through the network, enabling effective training. And conceptually, it approximates a threshold unit, outputting the values close to 1 or 0 for extreme inputs, which the binary decision making. So while newer functions like ReLU has become more popular in deep networks, the sigmoid function, which plays a vital role especially in output layers for binary classification. So the sigmoid function is defined as sigmoid of x equal to 1 by 1 plus expression of minus x, exponential of minus x. So it is a derivative plays a crucial role in training neural networks using gradient based methods like backpropagation. The derivative of the sigmoid function is sigmoid of x equal to sigmoid of x into 1 minus sigmoid of x. This elegant expression means that once we compute the sigmoid value, we can easily get its derivative by multiplying it with 1 minus itself. So this derivative is always positive and lies between 0 and 0.25, which ensures smooth gradient flow. So however, for very large or very small input values, the gradient becomes very small, leading to the vanishing gradient problem, especially in deep networks. Despite these limitations, the sigmoid function remains a foundational tool in machine learning, especially in binary classification tasks and output layers. Tanh function. So in short, for hyperbolic tangent, another classic activation function in neural network. Like the sigmoid function, tanh squashes its input, but instead of mapping values to the range between 0 and 1, it transforms them into the interval between minus 1 and 1. This makes tanh 0 centered, which can help with optimization and gradient flow, especially compared to sigmoid, which is always positive. As the input nears 0, the tanh function behaves almost like a linear transformation. But as the input moves further from 0, the output saturates, approaching minus 1 or 1 depending on the sign. Visually, the tanh curve resembles the sigmoid curve, but with a key difference: it exhibits a point symmetry about the origin. This symmetry allows it to better model data that has both positive and negative distributions. So in short, tanh is a powerful activation function that balances smoothness, nonlinearity and symmetry, making it a strong choice in many deep learning architectures. The tan h function or hyperbolic tangent is defined as tan h of x equal to exponential of x minus exponential of minus x divided by exponential of x plus exponential of minus x. So already we know that. So it is a derivative in both elegant and practical for training neural networks. The derivative of tan h is tan h of x equal to 1 minus tan h square of x. This means that once we compute the tan h value, we can easily find its derivative by squaring it and subtracting from 1. This derivative is smooth and always positive, which helps to maintain gradient flow during back propagation. Like sigmoid, tan h can suffer from vanishing gradients for very large or small inputs, but its zero-centered output often makes it more effective in practice. So in short, the tan h function and its derivative offer a balance of non-linearity, symmetry and smoothness, making it a valuable tool in deep learning.